let's talk about rare earth elements. Hi, I'm the Alloy Geek, and in this video, we're going to talk about how Handheld XRF can measure rare earth elements in the field and in the lab. Now here I have a portable test stand that's easy to travel with in the field. This is the field test stand or field mate test stand by Evidence Scientific. It works great. You can see the Vanta Max is actually in there, and I'm going to be using that for this video. There's also a benchtop test stand or a workstation here, which is a little bit better for a lab. It's a little less portable, although it does disassemble and you can take it out there with you. Now, I have some certified reference materials and I have a whole kit of them, but we're just going to test a few of them today and compare the results for what we actually get on the Vanta Max to what the certified value is for each one of these reference materials. And then we'll be able to look at across a broad range and two different matrix of materials. We have both uranium and lithium-bearing ores here, how the Vanta Max performs out of the box. Now, I did not apply any cal factors. I did not ask for Evident to smith the data to look better. What you get is going to be average data of about 5 shots with XRF on each one of these certified reference material. And my goal is to help educate you on what you want to buy if you're looking to bring in a Handheld XRF to specifically look for and measure rare earth element concentrations. So what elements are we talking about? We're talking about lanthanum, cerium, yttrium, praseodymium, neodymium, samarium, europium, and gadolinium. And the science gets a little bit complicated when you start getting into these rare earth elements, even on XRF analysis, which is typically a pretty robust science. We end up with a lot of matrix effects and interfering elements for those specific rare earth elements, given that there's only certain peaks available to look at. So without further ado, we're going to use a 3-beam geochemical mode here, which is going to be running for 90 seconds of time on each beam mode. And that's going to allow us to compare the data in the field really easily. So first up here, I'm going to actually test REEs 104. Let's find that sample. All I need to do is place it here on the Vanta's field stand. Now keep in mind, this area where the window is needs to be free of powder. If you're in the field, that can actually be kind of challenging. I'd recommend making sure that your surface is really clean, because you can contaminate it and see some false positives if you maybe have soil sitting on that window or on that area. So now that the sample is loaded, all we have to do, we are in Geochem 3-beam, perfect, and we're gonna hit go. I've already configured the times for this test. When the red lights are on, the X-rays are on. And what the Vanta Max is doing now, it is actually shooting X-rays into the sample. Now, one of the things you may not be familiar with when you're using a 55 kV beam, which is beam 3 by the way, and if you're doing soils analysis on an Evidence Scientific device, beam 1 is the 55 kV on the soils analysis side, but on the geochem side, it's beam 3. So right now we're looking at some other elements like titanium, barium, zirconium, and manganese, thorium, uranium, things like that. Anyways, back to the original point, your sample cup should be full all the way. The 55 kV beam is going to give you more penetration into your sample, and you want to make sure that you're filling your sample cups with enough material to actually get a result. So if you're looking at only maybe, we're talking the differences, fill the cup with, almost all the way up, which is 20 to 30 grams of material versus 10 grams of material, which you can get by with most samples, specifically when you're running a very high power X-ray beam. So Evidence Scientific did send me the Vanta Max to review, and I did not accept any money for making this video, so regardless of what you hear out there, I didn't. I'm just doing this so I can help educate you on what to buy, and I want to see for myself firsthand how the Vanta Max performs on rare earth elements. These are things that we hear in the marketing literature, but how we actually see them in the real world is going to be a little bit different. And the data, everything that I collect here today is going to be shared with you guys. Well, that may not be exactly true. I'm gonna run all the data off the camera because I don't want you guys to sit here for the whole duration. But the tests will be 5 repeat tests of 90 seconds per beam for each one of these 6 samples. That will give us a good idea over varying concentrations of rare earth elements, what kind of data we're gonna get from the Vanta Max. Now keep in mind, what that's also gonna do is tell us where maybe we missed the mark, and where we see matrix effects in materials, and where we may even need to apply cal factors in the field. The data that I'm also sharing you is out of the box data. I did not apply cal factors. I did not work with the instrument and really dial it in for each specific matrix. I want to look at out of the box data. The bigger most geologists, when they're in the field, they're going to be trying to dial in to their specific matrix to get the best result they can. I'm not doing that. So if you see trends where I'm consistently over-reporting a little bit and you're like, hey, you could adjust that, I know, but in the case for this experiment, I'm just gonna export the raw data and I'm gonna share it with you guys. Okay, so we just started the 55 kV beam here on the Vanta Max, and what you're gonna see down here, experiment 3 of 3, right? We're about 15 seconds in here. And when we start to scroll down, we're gonna look for those rare earth elements starting to pop up. So you can see ND is neodymium. It's starting to populate a value, and it's gonna take some time for that value to level out, but this is what the preliminary data is gonna look like, okay? So we're also seeing what other elements we have in here. It looks like yttrium, we're getting a good result on yttrium. And if we look at the actual certificate of analysis, which I have right here in front of me, I brought all the certs so we could actually have a conversation about this. Yttrium, we actually measure that at, I forgot, for this sample, for the REEs 100 series samples, there is no yttrium posted, but we do read some pretty consistent results. You're gonna see that in the data that there's gonna be a comparison between the certified value and the measured value, okay? And so for things like yttrium, where I don't have a published value, there's just gonna only be the actual value provided that we measured today in today's experiment. But lanthanum, 56 parts per million so far. It looks like the actual published value or certified value is 48.8 plus or minus 2.7 parts per million. So you can see our lanthanum value is approaching that real quick, and the longer we run the test for, the better our result is gonna get. Now, a couple of things with Handheld XRF here, we can only see certain elements, and there is a matrix effect going on here of some kind, and it may impact the results of some of our readings. But we'll talk about that later. Right now, what I want to talk about is the actual results. So this is what your result's going to look like when you're done, and you're going to have all your elements on the screen here. Now, a couple of elements we talked about today, things like Europium, Gadolinium, and Samarium. The matrix materials for these uranium-based ores and the lithium-based ores are interfering a little bit with the low concentration of those elements. So I'm really not able to report those in the tests here, which is a little disappointing for me, but I think it's good to know that we have some matrix effects here. It's also kind of difficult to find certified reference materials that really show those specific elements well. There's a bunch of them out there. REEs does a great job of providing those, but they are a little bit harder to find. So Praseodymium, we can see we measured and detected that. We've got uranium and thorium in some concentration, which means this is going to be a low-grade uranium ore certified reference material. So what we're gonna do next is we're gonna put together these results and show you what that looks like. Okay guys, so we have our data all put together here. You can see there's a ton of information in this area here. I've gone back and I've done a labeling of all the samples here, and then on the bottom I've done an average of all of those results. On this screen here, I've just basically put together graphs comparing the measured values of each of these samples with the sample names as well, so you'll be able to tell what certified reference material I ran and how close we got to it. I've run a few different certified reference materials within the same series, and the reason for that is they have different concentrations, and sometimes where the concentration of an element is somewhat fixed, it lets us see the repeatability of how well we're able to see that even as the other element concentrations vary. So the first one here is yttrium, which is a pretty easy element to see with Handheld XRF, and you can see we did a great job of measuring yttrium. You'll notice that the blue bars here, those are the measured values, and the orange bars are the certified values. And you'll notice for the 104, 105, and 106, we do not have a yttrium certified value. That's okay. You can see the correlation that we have within about 10 parts per million or less here with the orange bars, and probably some improvement here we could do is doing add some cal factors to really dial this sample into the matrix. But I'm not going to do that for this test. I'm just going to give you the out-of-box data. Next up, lanthanum. For REEs 104, 105, and 106, we're able to measure lanthanum with a high degree of precision. You can see for 147, 148, and 149, we have the same trend. We could possibly add a little cal factor adjustment here for the 140 series, but ultimately we have pretty good agreement, and if you found this kind of data in the field, you're going to be doing really well. Where you see a bigger gap in parts per million between what we actually measured and the actual values are in higher values of rare earth elements. Typically, rare earth elements are only available in very low concentration in the Earth's crust, and that's typical for exploration into what we see. When we start getting into 500 parts per million and above rare earth elements, I mean, you're going to be real excited if you find that in the field, but at the same time, we may need to add a different type of Cal factor adjustment to the instrument itself when we get into higher concentrations. But you can see the agreement on low concentrations, which is what this instrument is actually designed to do, is to shoot real world samples with a high degree of precision. And you can see it does exactly that for lanthanum. Now, cerium is an element that we're interested in. It's not exactly as interesting as some of the other rare earth elements, but typically when we're doing rare earth element exploration, we're finding cerium in the field and we're measuring it. It can actually interfere with some of our other elements as well, so it's good to measure and know the concentration. You can see here again, blue bar is what we measured, orange bar is what the certified value is. We have really good agreement with cerium. Praseodymium is one of the first elements that is, I think, really exciting to see. Here we have a few different values that we measured. Now the Arraeus 104 sample has 12.8 parts per million. We did not see a result there. Our result was below the limit of detection of the instrument. I probably could have run the test longer or made some other adjustments to actually get a value there. So a 90-second test really just didn't nail that exact number. You can see there's even some variation on these other low concentrations at 20 parts per million and below, which is pretty low concentration for rare earth elements, still, but we're able to at least detect the presence of them. I'm not showing you guys the statistics here. I'll give you an example on Arraeus 104. The plus or minus on the certified value is 12.8 parts per million certified with a plus or minus of 0.7. And you can see that for the Arraeus 104 here, I guess that's rounded to, yeah, okay, so that's right, okay. It does increase for some of these other ones. So for example, Arraeus 147 here, we have for Praseodymium, looks like that's on the next page, 122 parts per million. We've showed the actual value here of 121.631, but plus or minus 9 parts per million overall with 3 standard deviations of, so 9 parts per million, that puts us within the standard deviation of the certified reference material there for Praseodymium, which is really good. I'm also not showing the instrument uncertainty either here in this column, but I think you get the better idea for the nominal values here. Now, on Arraeus 149, you'll notice that we do have some interference going on with Praseodymium. I'm not exactly sure what that is. I'd have to do a little bit more digging, but I'm not gonna manipulate the data to show you otherwise. This is an average of 5 results. There is clearly some sort of interference here going on with the Praseodymium result. You can see how it differs from the other ones in this matrix. So maybe a little bit more investigation there. If you have any insight as to why that might be happening, feel free to post a comment down below. Neodymium. Neodymium is a very interesting element for most people looking for rare earth elements. It's really popular, has a lot of uses, and you can see how consistent we are with the Arraeus 104, 105, and 106 samples. The Arraeus 147, 148, and 149, we also have really good agreement as well, with the orange being the certified and the blue being the measured value. So we're able to measure these rare earth elements with a high degree of precision with the Vanta Max 55 kV. Now, after neodymium, you might be asking yourself, well, where the heck is samarium, europium, and gadolinium? Well, actually, in the certified reference materials that I chose for this experiment, apparently samarium, europium, and gadolinium are all kind of hidden elements given the matrix effects of what's going on and the low concentration of those elements. So we weren't able to actually measure those elements. They were below the limit of detection, or they were lumped into another category behind the scenes due to some interferences in the matrices. So in the future, I may be able to find some samples that have easier time reading samarium, europium, gadolinium. It's actually kind of difficult to find certified reference materials to look at those specific elements. They're not typically commercially available. All right. So that's it, that's the data here. What I want to do next is publish this data and show it so you guys can download it and take a closer look for yourself. If you're a scientist in the field considering a handheld XRF for your exploration or for your mining application, and you're wondering if the Vanta Max is going to work for you, I would take a look at the data and let that drive your decision. I think we had some really good data here today. So there you have it. That's an X-ray experiment for a 55 kV X-ray device. This is the Vanta Max by Evidence Scientific, and I think we collected some really good data here. This is real world data. So these samples come from lithium and uranium-bearing ores. So we have two different matrices here and some different concentrations of rare earth elements, along with some that are relatively the same. We're able to look at the repeatability of each of these measurements today from like a 10,000 foot view. And we were also able to see how the analyzer did with different matrices. I think it did a great job, and we were able to get some good repeatable data. Now, a couple of things I'd like to do in the future is look at Samarium, Europium, and Gadolinium. I know we didn't get to that in today's video, but it's actually kind of difficult to find certified reference materials which showcase those elements really well. In the field, a Vanta Max like this is going to work really well for an exploration handheld XRF, and the 55 kV tube is going to give you better results on things like the rare earth elements, lanthanum, cerium, praseodymium, neodymium, things like that. And it's going to unlock the ability to see things like samarium, europium, and gadolinium. Most of the geologists that are out there in the field know that you need to add cal factors for your specific matrix. So if you have two different matrices, you'd operate with different cal factors. None of the data in this test has had any cal factors added to it. This is all just out of the box data to let you know what the analyzer is doing. And if you can clearly see trends that you can adjust for in the field, I encourage you, that's an encouraging sign, because that means that you can dial the data even more into your specific matrix. Thank you guys so much for watching. If you have any questions, reach out to us on alloygeek.com, and we'll see you guys next time.